Hello. So today I would like to talk a bit about the Zcash transaction model, and basically what we need to know in order to do a light wallet. And so this video or talk will be a bit more technical than the others, and this should give you enough information to understand the LibRoss Zcash and the WarpSync code base. So the primary source is the protocol documentation, which is this one. This is quite first of all, it's a very long paper. Yeah, more than 200 pages. More than 200 pages. Yeah. Even though most of it is in the annex, and it's talking about the zk star circuit. Starting from 185, it's still a pretty dense document, and honestly, you don't need to know all of that to understand how the light wallet operates, or how the light wallets operate. But you still need to do quite a lot. So let's get started. First of all, the one thing we need to know is that the model of Zcash is very similar to Bitcoin, and it's based on the concept of unspent transaction output, so UTXOs, exactly the same way as Bitcoin. So there are basically two main models, either the account model or the UTXO model. The account model means that, like Ethereum, you will have an address, and the address will track incoming and outgoing transactions, but the storage, the data that you keep is at the address level. And so then you can query the state actually is at the address, where in the Bitcoin model, address don't really exist, and you have a bunch of nodes that are transferred, created and destroyed, and transferred between users, and then the users are identified by an address, but addresses are like more a byproduct of the protocol than something inherent to the protocol. So if you could want to have an image of what a node is, it's pretty much the same thing as a shake. If you feel a shake, and you give the name of the person who receives it and the amount, and you sign it, you see that you actually can put any amount you want. You can put pretty much any person destination you want, and then you have a signature that authenticates that this is really coming from you. So the idea here is that contrary to bank notes, which have a fixed denomination, so $5, $10, and so on and so forth, the shake, you create them, and they have any denomination you want. So when somebody receives a shake, instead of going to the bank and then putting it into account, they're gonna trade shake directly one to another, right? So the transaction is basically a series of shakes that you have received, and then a series of shakes that you are emitting. So the only difference is that you're not caching these shakes anywhere. You are using them directly. So in the model of Bitcoin and Zcash, most important things that you really have is the amount and the destination. So in Bitcoin, destination is actually a script, but for all intent and purposes, the script is for the most part is associated to an address. So there's some kind of mapping between the popular script and an address. But for Zcash, there's no script, and the node itself has an address. Okay, so where is that stuff? Okay, so the thing with Zcash though, that the nodes are then encrypted, and that's a key difference, right? So there would be a notion of a plain text node, which is like the content of the node before encryption. But what you would see on the network would be encrypted. But it's important to know how a node looks like before it's encrypted. But where is it? Here. Okay, so we need to simplify a bit because this is pretty complicated, right? First of all, we don't really care about Sprout and Orchard, so we are looking at sapling. So sapling is like that, right? We recognize a few things. We recognize the V is the value of the node. Recognize the memo, which is arbitrary text. And we have D. So D is essentially the address, right? So when you talk about an address, you're actually talking about a point on the elliptic curve. So D is kind of like that point. So this is your address. Lead by is simply a differentiator. It's like a version byte. So you have address, you have the value, and you have this guy. We're going to see it later. But it's basically a random number. So this whole thing together makes your node unique. So without this dude here, this RC, if you had two guys paying you with the same amount and the same memo, that node will be exactly the same. So we need something that makes the node unique. That's the kind of the purpose of that RC. So nothing really like different from what we would expect, but it gets a bit harder, of course, because nodes are encrypted, right? And then we can go back to the encryption part. Once they are encrypted, they are called output description. This guy. Is there anything simpler than that? Yeah, this one. So action transfers and description, this is for Orchard, so we don't care about that. Okay, by the way, the only thing we care about is the green text because the sapling. Well, the black text is common and the green text is for sapling. Okay. Alright, so when you encrypt, I don't know if it's really here. Okay, let's assume it's not here. What you use is you use your encryption key, right? And the encryption key is something that is called IV key. It's derived from your address. So if somebody sends you a note, he knows your address. So from the address, he can derive he can create an ephemeral key. So each node will be encrypted with a different key, and it uses encryption that is symmetrical. So knowing the key, so there's only one key per node, you can encrypt and decrypt. The algorithm is called CHA-20. There's another very popular one. You may have heard of it. It's AES, Advanced Encryption System. AES. But this one uses CHA-20. So that encryption key is then stored in the transaction, in the output. Sorry. Let me see where it is. Sapling. Sending nodes. This must be this one. Okay, so you can read this part here. But basically what's going on here is that there is okay, so there's the key that's going to be used to encrypt the node, and that key has to be kind of derived from your address, so that you, if you receive, okay, let's make it easier than what it is. The protocol is quite complicated. So what you want is that if you give the address to somebody, he should be able to pay you, right? So he should be able to derive a key that he would use to encrypt your node, and with that key, the incoming viewing key, you can identify or decrypt nodes that are coming for you, right? That's why they're called incoming. So that key will only be able to decode nodes that you receive, right? So you will not be able, for instance, to decode nodes that you have emitted in the past. So let's say that you have A and B, A pays B. So A knows the address of B, he makes a transaction to B, then that transaction goes to the blockchain. B scans the blockchain and then tries to decrypt everything that goes by. So one of the things is that once it's encrypted, there's no way to recognize there's no envelope or nothing that is in clear text that identifies the destination of the node. Therefore, if you're B and you don't know in particular which node you have received, you have to try to decode everything that goes by. So 99% of the time, this will not succeed. This will be nodes for other people. So that process is quite expensive, but that's the way it is because we want to ensure privacy. But 1% of the time, for whatever, right, you will be able to successfully decode the node, and then you will have the plain text information, which is the value, the seed, and the memo. Right? These three things you would get. But from the point of view of A, the guy who sent you the node, once it has been sent out, assuming now that A doesn't keep any external bookkeeping information, no database records or anything, he will not be able to recognize that node anymore. He has his own incoming viewing key for receiving payments, probably, but that is completely unrelated to whatever incoming viewing key was used to pay B. So this is asymmetric in the sense that you make the payment, but only one side is able to decode that payment. So in addition to this mechanism, because you can see that it's a bit inconvenient, if A loses the record, or if A wants to identify which payments he has made, he will not be able to do so. So there's a second key which is called the output viewing key, so OVK, which allows A to decode the same transaction. So that transaction, there's a special provision for that in the protocol, basically, which allows user A, using the OVK, to decrypt the node that he sent to B. Right. So now the trick here is that the OVK that he's going to use is going to be his own OVK. Right. If he uses the OVK of B, then it doesn't help him anymore because he doesn't have that OVK. The OVK of actually he's not even able, because the OVK of is not part of the address. Right, so we have to remember here, right, that's the IVK when you make a transaction from A to B. So we're only talking about the output of that transaction for the moment. That output of the transaction has a node that is encrypted with the incoming viewing key of B, but the output viewing key of A. Right? That's one thing. So that pretty much covers the output side. Right? There's other things like binding signature or this stuff, but for the our level of understanding, we just need to be aware that that's what you have, right? In the output description. Now the only thing is that if you only have this, if you have a wallet that only scans for this kind of stuff, you will only be able to detect the money that you receive, the notes that are incoming to your wallet, and you would not, of course, be able to see whether you have spent anything. So this is actually the problem of the Zondax hardware wallet. They give the IBK, but they don't. That's it. So you know which IBK to scan for. So you can make a wallet that uses that IBK and scans the blockchain, detects every payment that wallet received or this account received. But you will not be able to know if that node has been spent later. So that's the second part, right? So the second part is how you say that you are spending a node. So obviously there's a part which says, okay, I'm spending a node, so I have to sign it, right? So you have to prove that you actually know the secret key that corresponds to that particular output. But before even that, you need to be able to indicate which node you are spending, right? So in the case of Bitcoin, which is not encrypted, this is a fairly simple process. You have all the nodes so blockchain is visible by everyone. So everyone can keep track of all the output of transactions, right? And you can simply say, okay, I want to spend that particular previous output by giving the transaction ID and giving the index of the output in that transaction. So output can have like 10 the transactions can have 10 outputs. Usually they will have more than one, one for the recipient and one for the change. So at least two, not at least, but most of the time it's two. So you just indicate the transaction ID and the index of the output in that transaction, and then of course you have to sign it. So for Bitcoin, it's very clear how to do it. But for Zcash, we don't want they don't want to say that, hey, this is the node, even encrypted. We don't want to point towards a given node, because that the fact that you are telling which node you are spending gives some kind of information. It gives the age of that node, because we can figure out which block it was in. I don't know what else you can really derive from that, but this is already more information that we want to provide. We want to give absolutely no information, right? So, but we also don't want you to artificially create money. Say that, okay, I'm spending a node X, but that node does not exist. So that would be like creating money. Or we also don't want you to double spend, to say that you spend X and then later you spend X again, right? So the second mechanism, which is to avoid this happening, so this is about spending nodes, and that's actually more complicated in a sense, right? So we're also going to simplify a lot here. But what's going to happen is that when you create a node, right? When anybody creates a node, the node has a hash value. So and that hash value is unique. Right? You don't have two nodes that can hash the same value. So what as a protocol enforcer, as a Zcash node or client, a full client, what you need to keep track of is all these node commitments, node hashes. So these nodes, you can't read them, right? I mean, you can read some of them, the ones that were for you because you have the IVK, but for all the other ones, you cannot read them. But you still know their hash. And you know that if two nodes are identical, they will have the same hash. So this already prevents people from from spending the same stuff twice, right? Because if they spend the same thing, they would give you the same node commitment twice, right? So that already partially solved the problem of double spend. Alright, so the second problem is that how do you prove that you actually are the one creating that node? So when you are node, node and node, right? When you are a client, let's say when you are a client, you have to keep track of a tree. You receive all these node commitments, and you are supposed to keep track of all of them, right? To make sure that there's no double spend, right? So you put them all into a data structure. So for time being, let's assume that it's not a complex one. It's just a list, right? So we keep them all in a list, and then and the list is ever growing. You never can remove any of them, right? So what then you do is that you okay. So another beauty of it is that the guy who creates a transaction will not actually give you the node hash, because then you will be able to track when that node was created, and you will be able to figure out how he's spending output from that transaction, right? So you keep track of all these nodes, but when the guy makes a transaction, he will give you a piece of information that doesn't allow you to figure out which node has been sent. But that information is through the Zcash NARC is enough to figure out that node was already is somewhere in that tree. So that's just the Zcash NARC statement that is expressed, right? So there's a second level of scrambling, if you want. The node itself is scrambled into encrypted, and then you get that node commitment. But when you get the spending information, you don't really get the node commitment. You get a proof that that information is derived from the node commitment, and that node commitment is somewhere in the tree, right? And that information is called a nullifier, right? So I hope that I explained it enough, but let's repeat it one last time, right? The flow is that you create a transaction, you pay somebody, you know that person's address and how much you want to pay, so that forms a node, right? That node you will encrypt, and that becomes something that would go into the blockchain, encrypted. With that encrypted node, you will also have the commitment, which is basically the hash value of that node. The clients are assumed to keep track of all the node commitments that go through. Right? All these nodes are going to be kept as a hash of a fixed size, so everything can be stored, because we are not able to figure out which ones were used. Actually, you know which ones you have used, but you don't know as the overall system state which ones of these nodes have been used. What you know though is that if somebody spends and you need to verify that he's not cheating, he's going to give you a nullifier. So that nullifier is going to be derived from the node, the node plaintext actually, and that nullifier, therefore, because it's derived from the node, has to be unique. It is going to be unique. He's not going to derive a second nullifier, right? So what you do, right, is that with the nullifier and the Zcash NARC proof, the Zcash NARC proof will say that indeed that nullifier is referring to some node commitment from that you have received before. so that you verified from the Zcash NARC, and that therefore this nullifier is valid. And then that nullifier, you have to keep track of all of them, because if somebody is trying to double spend, he would be forced to generate the second time the same nullifier, and then you will see that there's a double spend on the nullifier because the nullifier was used before. Right? So all this stuff about nullifier is for pointing out in zero knowledge that you are actually using a node that was yours. Right? And then there's another fancy statement or crypto statement that enforces that the amount of incoming nodes, what you are spending, balances out with what you are paying, plus the fee. Right? But that's another stuff. Right? So we don't. If you're a light client, you don't need to care about so much, right? So, but you need to know about what I've told so far, and I think it's already much more complicated than the other coins. So we got to the point where this is unfortunately what you need to know, right? You need to understand what a node is. You need to understand what's the IVK and what's the OVK. You need to know what's the difference between a plain text, a plain node, and an encrypted node. And then, therefore, you need to know what's the output description. You need to understand what's the nullifier and how they relate to spending descriptions. So that's pretty much it, right, for this. As a client, as a light client, you're not going to do. Light clients actually have it easier and harder, right? The easier part is that they rely on the full node to do most of the heavy lifting. They will not keep track of all the node commitments. Right? This is not this is part of validation, and this is not part of their job. So that's something they don't have to store. But it kind of makes it harder because they need to be able to generate the information needed to compute the Zcash NARC, while not having the entire set of information that a full node has. So basically, a full node has it's like an accountant that receives every paper from everyone, right? So sure, it's a lot of work to keep track of all these papers, but when you want to have a signature, when you emit a fill of form, you know that he knows that he will have enough information to fill that form. Whereas if you want to say, okay, I'm gonna throw 99% of that stuff away, sure, you will have less paper to keep track of, but then you have to make sure that you're not throwing away information that you need, right? So that's where things get hectic, right? And that's where there's this WarpSync comes in. We are trying to make it more optimal and keep less information than a regular light wallet. So the information we are calculating will still be sufficient to generate the payment, to generate a Zcash NARC for payment, but will not be as complete as a full node, obviously, but also not as extensive as like the information that Zec Wallet or Nighthawk or the ECC SDK maintains, right? And by maintaining less information, we're also computing less information, and therefore we're going faster. That's one of the key points of this WarpSync thing. So I think I'm going to stop here because it's already pretty long. And the next time we're going to talk about what information we actually need to create a transaction. So before we leave though, let's recap a little bit. So for Light Wallet, there are actually basically three things you want to do, right? The basic functionality is being able to know your current balance. than the ability to receive money and the ability to send money out. So receiving money is obviously the easiest, since it's mostly a passive operation. As long as you give a valid address, the address that matches your wallet, it's not your problem who makes how to make the transaction, how to put it in the blockchain. So even a paper should be enough, right? So we have paper wallets that support receiving money. So that part is fairly trivial. The second part, right? The second and third part, knowing your balance and making a transaction out is where the stuff becomes really tricky. So for most coins, they are both about the same level of complexity. If you know your balance, then you are able to make a transaction out with fairly the same amount of difficulty. For Zcash, that's not the case at all, right? That's where I think there's a lot of misunderstanding or misconceptions happening. When you want to receive, when you want to see your balance, you just need to track, but you need to identify incoming nodes and outgoing spends, right? So that's okay, right? We kind of saw how we do it. We recognize the incoming nodes by trial decrypting them, and somehow we keep track of, we can recognize our nullifiers, right? So there will be nullifiers going floating out. All these transactions will have nullifiers. If there's a way for us to figure out which nullifiers are ours, then we can recognize our spends, right? So these are, I didn't say how we do that, but assuming that we know how to do that, the second part, first part I think is very clear now, then we know how to calculate the balance. Now the last part, how to make a transaction, is where this is very hairy, because the Zcash NARC, part of making a Zcash NARC is pointing out to your node inside that big list of nodes, right? All these node commitments, you know which one are yours, you know which ones you want to spend. So to create that proof, the Zcash NARC proof, the algorithm requires you to identify which one it is, like node number 1005, for example. And not only that, but you need to give a set of information that changes every time a node is added. So this information that you're building keeps changing for every block, every transaction even, will change that information. So every node that you have that you want to spend, your wallet, your Light wallet, will have to keep track of that particular information per node, and it has to be updated. It changes for every transaction. You don't have to update for every transaction, so she's also part of WarpSync. But you have to you have to update for each transaction, but you don't have to store the update for each transaction, because basically it's at the point where you want to spend that you need to give that information, right? So let's say, for example, that the information goes, this is the color, right? It's red, blue, green, blah, blah, right? So basically the color keeps changing of that node. The color associated to that node keeps changing whenever there's a transaction. So the transaction says, okay, go blue. So the node goes blue. And the next transaction says, okay, node go red. So it goes red. The idea is that when you want to spend, you need to give the color, the current color. So you will have to say, okay, that node now is red when I make the transaction. But WarpSync, the difference between WarpSync and the regular sync is that it will not store, it will not even calculate the intermediate state. It doesn't care whether you want blue and then red. What matters is that it's red at the end. So it would jump from being so yellow originally, then blue and then red. It will go from yellow to red, right? And then you will emit exactly the same information. That's why your transaction is correct, but it didn't have to go through the blue state. And that saves a lot of calculation. All right, so that's kind of like a taste or the preview of the next topic, which will be more about how we do this coloring thing, right? Of course, it's way more complicated than the color, but I think the essence is that, right? All right, so I hope it was informative, and I would try to record the next one as soon as I can.